Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is to just kind of build off of what we started talking about last time with these abstract vector spaces, and I want to show some more connections between what we've sort of studied this year with other linear algebra concepts and show how they connect to abstract vector spaces. So one of the things we talked about last time briefly was the span of these abstract vector space problems. And so you can do things like this. You can say, like, is cosine 2x, this function, in the span of these two functions? And so these are like, you think of these as vectors, okay? Vector is a very abstract thing in reality, much more abstract than like numbers in a table, basically. All we're saying basically when we write this stuff down in math is saying, like, can these things be built together to get cosine 2x? And yes, they definitely can. There's a trig identity that says cosine 2x is equal to cosine squared x minus sine squared x. This is basically just like the analogous problems say, like, just make one up, is the vector 2, 1 in the span of 4, 3, and 2, 2, and yes it is, because you can say 2, 1 equals 4, 3 minus 2, 2, right? These two span some sort of plane, basically. Well, they're R2, right? And this is another vector in R2 that you get by doing that same subtraction. So this vector is like this one, this vector is this one, this vector is this one. So that's basically the idea with these things. So this would also be under this would be in the vector, the abstract vector space of, like, what they call this script F, which is really just the set of all real valued functions. And so basically we're thinking like over R. So, basically plug in real numbers here. That's how we're thinking of this. So let's take a little more complicated of a problem here now. So let's try to figure out, is sine 2x in the span of sine x and cosine x, okay? So, abstractly what that means is, can we do something like this? We have like c times sine x plus d times cosine x. Can that happen for some c's and d's? This has to hold for, like any x's, right? And so, the idea here is basically, let's pick some x's and see what it tells us about c and d. So if we do, let's say I want to take x to equal 0, right? Then sine of 2x is just 0, right? And sine of x is also 0. So it's like c times 0. And then cosine of x is 1, right? So we have d times 1. So this would imply that d equals 0. So if x equals 0, d equals 0. Right? Let's just do another one here. So let's take x to be pi over 2. Just picking nice x's that we can deal with, right? So then it's going to say sine of pi, right, which is equal to 0, is going to equal c times sine of pi over 2, right, which is 1, and then plus d times cosine of pi over 2, which is 0. And so here, what this implies is that 0 equals c. And so now what we're basically trying to do is say, can we have sine 2x equal like 0 plus 0, because we got both these to be 0, for all x, right? And obviously that's a no, right? That's a silly statement. You can't get sine of 2x to equal 0 for all x, right? For some x, you can do it, right? But for that one, you can. but yeah, this is why sine 2x is not in the span of sine of x and cosine x. There's no trig identities that combine sine of x and cosine x in some clever way and get you sine of 2x. It's not possible. So what this kind of argument shows is that no, sine of 2x is not an element of the span of sine of x and cosine x. So that's kind of like a counterexample in a sense too. Not a counterexample, but it's like an argument just as to why it's not in there. So what I haven't talked about yet, but is pretty intuitive with these abstract vector spaces, is the idea of linear independence and linear dependence. So the good news is this definition is like exactly like what you've seen before. So a set of vectors, and these are just what you want to like let your brain kind of abstract now. So don't think just tables with numbers. Think all sorts of different things, literally anything almost. So is a set of vectors here is linearly dependent if there are scalars c1 through ck, at least one of which is not 0, such that this whole combination of them equals 0, right? Standard definition of linear dependence. And if the only way to make this equal 0 is have those coefficients be equal 0, then like all of them, then it's linearly independent, okay? So we can take problems like this. So P2 is the vector space of polynomials of order 2. The coefficients here are coming from real numbers, basically. So this would sort of be understood as like P2 over R. And we could ask, is this thing, this set of quadratics, linearly independent? Or can you maybe build, one of these quadratics out of other ones, That's the idea. And the way to do it is, honestly, to just think about these things as tables with numbers. It's really the tool that we've learned to solve these problems. One way you could do it is just try and come up with like a times 1 plus x squared plus 2, b times, b times 1 minus x plus 3x squared plus c times 1 plus 3x minus x squared. And you want to basically set this equal 0, and like you could distribute in, combine like terms, do it all that way. But we can use our tools that we've already learned. We can basically take this first quadratic and think of it as just the vector. It has 1 in the constant, 1 in the x component, and 1 in the x squared. So it's kind of like a 1, 1, 1 vector, right? This next one has 1 in the constant, negative 1 in the x, and 3 in the x squared. And this last one is like 1, 3, negative 1, right? And so the faster way to do this problem is to just be like, okay, I want to augment 1, 1, 1, 1, negative 1, 3, 1, 3, negative 1 with 0, 0, 0, and basically just RREF. So actually, let's just do this. RREF. So basically we're thinking, what amount of these, like what I solve for will sort of be my A's, B's, and C's, which represent how many of these things I need to get to that. Or maybe I won't be able to do it, and the only way I'm going to get it to work is if, C1, C2, C3 are all 0, okay? If you RREF this one, you get that, and from that, most importantly, from this part, right, there is a row of zeros, so there's some sort of dependence going on, right? The only way you would get linearly independent is if you had the identity matrix here, right? You'd have a 3 by 3 identity matrix, so it'd be saying C1 equals 0, C2 equals 0, C3 equals 0, but we don't have that. So this is like really quick, easy way to solve a problem that seems really complicated. If someone asked you, can you build this quadratic out of these ones, right? I might just jump to this kind of argument quick and be like, yes, because I can see that like there's some sort of dependence relationship going on here, so I shouldn't need 3 vectors. I should be able to get to this one by just doing some combinations of this one, these 2, I should say. And this thing would actually even tell you the way to do it, right? But that's the idea. Here we can just see, since there is a 0 row, there is a linear dependence going on with those 3 quadratics. So abstracting this a bit more, if we take this set, which is sort of just our building blocks, right, of nth degree polynomials, and we were asked to show that it's linearly independent, the way I would just think about it is this forms a matrix that just is sort of our like classic example of a linearly independent matrix. So we have 1 and then in the constant for that first vector, and then nothing for x, nothing for all the others, all the way up to nothing for the nth one. Then for x, right, we have 0, 1, and then 0, and then a lot of nothings, right? Nothing in the nth one. And like just so on and so on, right? You get 0, 0, 1, dot, 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 0. And you could just like keep doing this all across, right? The nth one would look like 0 all the way down, and then you'd have a 1 in the bottom, right? And I guess we'll just... And what this really is this is just equal to the nth order identity matrix, right? And oh wait, I'm sorry. No, it'll be bigger than that. It'll be the n plus 1. It'll be the n plus 1 identity matrix. Either way, the point is, if you RREF this thing, there's nothing to do, because if you RREF, right, you basically just go right back to what you started with, and that is exactly what it means to be linearly independent. This is like tied in with this. So what we actually have right here is a basis, right, for that vector space, right? So we need 2 things for a basis. We need that my set spans the vector space, and then we need that the items in that set B are linearly independent, right? And so you just want to think about it in terms of like building blocks. For P2, we need a constant, we need a linear term, and a quadratic to build up any sort of quadratic we want, right? This is just like analogous to the set of like E1, E2, E3, where E1, E2, and E3 are like your standard basis vectors that you're used to. Your I hat, your J hat, and your K hat for, colors, for R3. So these are your building blocks for P2, just like these guys are your basic building blocks for R3. For that nth order polynomial one, it's the one we just had. We'd have 1x dot 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 all the way up until x to the n, and in here there are n plus 1 items, and so this is actually going to be similar to our n plus 1. Okay. M2 by 2 is, so this set right here is basically just the set of, typically in this course we think real valued matrices, but it's basically a 2 by 2 matrix. square matrix A, B, C, D, and that is actually a vector space. If you go through all the properties of it, you would get that this thing truly is a vector space. And to build up any 2x2 matrix, right? For that one, a basis could just be a simple thing for a 2x2, is basically the set 1, 0, 0, 0, right? Then 0, 1, 0, 0, then 0, 0, 1, 0, and then 0, 0, 0, 1. And so here, right, you can see you got 4 things, and so that's probably like R4. And it really is, and we'll actually get to a point where we talk about this symbol actually is a very important symbol in math. We'll talk about it, something called an isomorphism. But you actually can formalize this connection where you say this vector space is not just similar to this, but actually functionally the same. And so the math that we do here in R4 is actually going to apply to everything that we do here, which is super handy, super powerful. And that when we get to that kind of stuff, I feel like that's when I really started liking math. All of a sudden I saw the usefulness of so much of the stuff I had learned, and hopefully you kind of appreciate it too when we get to that point. But yeah, so the idea here is just like, this set of matrices, which are vectors, you can think of them that way. Basically you can just do A times that first one, plus B times the second one, plus C times this one, plus D times this one. And, you can get any sort of arbitrary 2x2 matrix out of there, right? Some A's, B's, C's, and D's, add them up, and you'll get any sort of 2x2 matrix. So when you're coming up with these, when you come up with a basis, you just want to pick one that spans the space and is linearly independent. You can't have a 0, let's say here, in every single one, because then you can never get matrices like, let's say, the identity, which starts off with a 1 there, right? That would mean that the identity is not in that span, right? So that's kind of the idea here with a basis. Just to sort of see it in practice, if you wanted to determine whether a given set is a basis, right, you can do this trick where you make vectors out of these matrices, like vectors in the way that you think of them. So 1, 0, 0, 1, right? And then here I would do 0, -1, 1, 0. I'm just reading top left to bottom right. And then 1, 1, 1, 1. And then 1, 1, 1, -1. And if I wanted to determine if it's a basis, one of the conditions is that they need to be linearly independent. So I could augment this with the 0 vector and basically solve this out with an RREF. If I do that, I would get, so you get that. And from this, right, this is just the, identity matrix in here. It's the 4x4 identity. And so that part implies that the set is linearly independent, okay? And then you would also need to do, so that's, I guess we did that, or that shows that the set is, does item 2 here, and you need to show that it spans it, okay? Then to do that, basically you have you have this. So we have, we've set up here, what I've set up is C1 times the first matrix, or vector, first matrix that is a vector, plus C2 times the second, plus C3 times third, and so on, right? And I'm basically setting it equal to like an arbitrary 2x2. And then from that, you can group like terms like this. I'm not sure actually if I should say group-like terms. I mean, basically all it is, right, is I'm just equating both sides. So I'm saying like C1, you know, right here, plus no C2 plus C3 plus C4 equals A, and like so on and so on, which now is naturally turning into a matrix problem. We would get this. You know, and this is something that we've actually solved before. We've done these things where we've asked, you know, are these vectors, do they span R4, right? And so what you do is you have to reduce this matrix, and if along the way you get something where you get a, you know, a statement that puts like A on the bottom or something of a fraction, then A can't be 0, and so then you get no possibility of having, you know, vectors that start with 0 here, so then it wouldn't be in the span. But turns out that this thing, basically, this thing has a well-defined solution, so it does span M2 by 2, or you can really think R4, because it's the same thing. So that would then, you know, this part with this part, it would show that this set actually does span M2 by 2. If you do the other one, okay, if you go and do the span part, what you're going to get at one is that, I realized I think I said the span part, but I meant the linear independent part. So if you just turn this into the vector 1, 0, 0, 1, you know, this into 0, 1, 1, 0, and so on, look at the top row here and the bottom row here. Those two things, when you do R1 minus R4, right, row 1 minus row 4, it's going to zero out. And if it zeroes out, then those things are basically not linearly independent, right? That would be a way to show that they're linearly dependent. This part is a lot of times an easier way to figure out if it's not going to be a basis, because it's a much quicker computation. Doing all this can take a little longer, definitely. So I would always recommend, if you're trying to show something's a basis, do this first, RREF everything, get the matrix out of it, and basically if it's an identity, linearly independent. If it's not, then dependent. And maybe you'll even see something like this where the rows, you know, maybe some rows are going to cancel out and you're going to get a 0 row, and so it's dependent, and that kind of thing. But that's kind of how you work with showing something as a basis given these abstract vector spaces. So the last thing I want to do is actually not really related to span, linear independence, or dependence, or basis kind of stuff. I just wanted to kind of go back and really just prove something that shows a good technique that we've seen before, but I feel like we haven't seen it in a little bit, and I wanted to do it again here. So I want to prove that every vector space has a unique 0 vector. And pretty much every time you see this word unique, you want to do a proof by contradiction. All right? And so what we're going to do is we're going to suppose 0 and 0 prime, let me actually rewrite that, are both 0 vectors. Let's say in V, my vector space V. Okay. Then by definition, of a 0 vector, then I have like some you know, other vector x plus 0 equals x, and x plus this 0 prime equals x for all x in V. Okay. But 0 prime is part of V, So I should be able to do 0 prime equals 0 prime plus 0. And then from that, right, I do have a property with vector spaces that addition, this operation of addition, however you define it, is commutative. So basically I can switch things around, 0 plus 0 prime. This is just, again, because in vector spaces, addition, and don't think of that addition as the one that you're used to. It can be all sorts of different things. Addition is commutative. Okay. So at this point, then what I'm going to do is I'm going to use what we know about adding a 0 vector to something. So since 0 prime is a 0 vector, right? 0 plus 0 prime should equal 0, right? So right here, it should reduce to just 0. But if you go back, right, the important part is right here, and then now over here, right? Note this shows 0 prime equals 0. So, assuming there exists 2 was wrong, and hence 0 vectors are unique for all vector spaces V, something like that. So it's just a good kind of classic proof technique to show something about uniqueness. So whenever you see this term uniqueness in math, classic go-to is basically to assume it's not unique in a sense. We're going to assume the, contrary to that statement, and we're going to say that there's 2 of them, and then we should be able to do some sort of math and arrive at some sort of contradiction. And so then what we assumed is wrong, and hence, in this case, then there's only 1 of them. So that's all I really want to show in this video. Hopefully you kind of saw that span and linear independence are really very similar to what you've seen before, even for these weird abstract vector spaces.